Hi, I am Sanjay Patel. In this video, we are going to discuss some theorems on successive differentiation. These theorems provide the nth derivative formulae for some standard functions. So in this direction, let us consider the first result, say theorem 1. And first of all, I will consider the simplest function and the known function, that is y is equal to e raised to x. Let us consider this way. If y is equal to e raised to ax plus b, where a and b are constant, some say real numbers, then prove that the nth derivative of y, that is yn, is equal to a raised to n into e raised to ax plus b. Okay. This is to be proved for every n belongs to n. Okay. Now, as you know that if a result is to be proved for every n belongs to n, we will use the principle of mathematical induction. Here, all the theorems of this successive differentiation we are going to prove using the PMI only, principle of mathematical induction. In that, whatever statement you want to prove for every n belongs to n, that statement we call as P of n. So let us begin with P of n. Let P of n be the statement yn is equal to a raised to n into a raised to ax plus b. Remember that yn means the nth derivative, that is dny by dx raised to n for the function y. Okay. In this direction, the first step for applying the induction is we verify the result is true for, say, n is equal to 1. So let us take n is equal to 1 and understand what is to be done. For n equal to 1, I am required to prove y1, that is first derivative, is equal to a raised to 1 into e raised to ax plus b. y1 means the first derivative or dy by dx of the function y. So as we have y is equal to e raised to ax plus b, let me remove this. Y is equal to e raised to ax plus b. Its derivative, that is dy by dx, you can write as e raised to the ax plus b, and the derivative of ax plus b is a. So this I can write as y1, because dy by dx is y1, as a raised to 1, it is constant, into e raised to ax plus b. So it is proved that the result is true for n equal to 1. For n equal to 1, we are getting the exact result what is here in star. So therefore, we can write the conclusion that P of 1 is true. Okay. Let us now assume that the result is true for any fixed value of n. So suppose P of k is true. Suppose P of k is true where k is any fixed natural number, or k is any natural number. We fix it first. So if the result is true for k, that is we have pk means yk. So just we have to put n equal to k in this star, and we assume that this pn is true for n equal to k. So yk is equal to a raised to k into e raised to ax plus b. Let us call this as result number 1. We always call the statement pk, which we are assuming as true, as result number 1. Now what we do next is we differentiate 1, differentiate result number 1, say with respect to x. So what we get is yk plus 1, because if you differentiate y1, you will get y2. If you differentiate y2, you will get y3, and so on. So if you differentiate y10, you will get y11. Likewise, if you differentiate yk, where k is some fixed natural number, what you will get is yk plus 1. Okay. That is the derivative of the left hand side. We are differentiating both the sides of this result number 1. Derivative of yk is yk plus 1. A raised to k on the right hand side is constant, it is as it is. And derivative of e raised to ax plus b is, as you know, a times e raised to ax plus b. And if we simplify this, what you will get is yk plus 1 is equal to a raised to k plus 1 into e raised to ax plus b. And what is this? It is nothing but pk plus 1. So we have proved that result is true for n is equal to k plus 1. For n equal to k plus 1 also we are getting the same result. Say yk plus 1 is equal to a raised to k plus 1 into e raised to ax plus b. You can check by putting n equal to k plus 1 in star. That is in the statement Pn. So this shows that pk plus 1 is true. Pk plus 1 is true. So what we have proved is this. Whenever pk is true, implies pk plus 1 is also true. So pk implies pk plus 1 is true. And therefore, we can say that p of n is true. P of n is true for every n belongs to n. So all these statements we always write in all the proofs at the end after proving the result by principle of mathematical induction. So the final conclusion is, as Pn is true, I can say Yn is equal to a raised to n into e raised to ax plus b is proved for every n belongs to n. So this is the first theorem, and one particular simple example to understand this. Say, if y is equal to e raised to 2x plus 3 is given, then find y10 of say 0. y10 of 0 means find the value of the 10th derivative. You know what is the meaning of y10? y10 means d10y by dx raised to 10, the 10th derivative of the function y with respect to x. So for this we use this formula. As in the above formula, just we put a is equal to 2 and b is equal to say 3. So we get yn from this as a raised to n means 2 raised to n. Just you have to put a equal to 2 and b equal to 3 everywhere in this formula. So this into e raised to 2x plus 3. This is the nth derivative of the given function. What is required here is y10 is required as y10 of 0, means the 10th derivative. First of all, we put n equal to 10. So y10 will be 2 raised to 10 into e raised to 2x plus 3 at any point. So this is y10, or you can also call it y10 of x, because y10 is a function of x. And therefore, if you want to find the value of this 10th derivative at 0, y10 of 0 is 2 raised to 10 into e raised to 2 into 0 plus 3. That is 2 raised to 10 into e raised to 3. So this is the value of 10th derivative at 0. Likewise, if any other point is given, you can find the value of the derivative. Okay. So very simple example based on that first theorem. Let us go to the next one. Say the second theorem, that we are going to prove about another popular function, that a raised to x, but we are going to write in a general form. If y is equal to a raised to say lx plus m, okay, where a is a positive constant, because for defining this exponential we need a to be positive for every real x. Then prove that yn is equal to yn is equal to l raised to n into into log of a to the base e raised to n into a raised to lx plus m for every n belongs to n. Remember, here n is involved in this statement. So we want to prove this for every n belongs to n. Okay, so again here also we are going to use principle of mathematical induction. So let us consider the statement Pn to be the thing which we want to prove. Yn is equal to L raised to n into log of a to the base e raised to n into a raised to lx plus m. Remember, even if we don't write the base of logarithm, whenever we don't write, it is understood that the base is always e. Okay, so this is to be proved for every n belongs to n. First of all, let us recall that for the basic function, if y is equal to, if we have a raised to x only, then we know that its derivative dy by dx is a raised to x into log a to the base e. Okay, so this is the standard formula what you have studied in your high school. Now we have written this function a raised to x in a general form, that a raised to lx plus m. So the power can be any expression like this, lx plus m. Okay, so the first step is we always verify the result for n is equal to 1. So for n is equal to 1, we need to prove the result is true for n equal to 1 from this. So I start with, we have y is equal to a raised to lx plus m. So we differentiate with respect to x. So dy by dx is a raised to something, derivative is a raised to something into log of a to the base e. Okay, into derivative of this lx plus m is L. Okay, for example, suppose if we have y is equal to a raised to 2x plus 3, then we write y1 as a raised to 2x plus 3 into log a into derivative of 2x plus 3 is 2. So like that. This we can write as y1 is equal to L raised to 1. So this I am writing first into log a raised to 1, log a to the base e raised to 1 into a raised to lx plus m. So therefore the result is true for n is equal to 1. We can verify by putting n equal to 1 in this Pn, in the statement Pn. Now proceeding further, we assume that this is true for n equal to k. We assume that p of k is true. So suppose pk is true. That means pk we can write as yk is equal to L raised to k into log of a to the base e raised to k into a raised to lx plus m. Okay, so this is our statement pk. Now you want to derive pk plus 1. Means we want to prove that pk plus 1 is true. So what we do is we differentiate this result. We differentiate result number 1 with respect to x on both the sides. In the left hand side we have yk, that means kth derivative of y. And if you differentiate yk, what you will get is the next derivative, that is yk plus 1. So we get yk plus 1 here in the left hand side. In the right hand side, this L and L raised to k and log of a raised to k, all these are constant. And that constant is in a multiplication, so we keep it as it is. So L raised to k as it is, and log of a to the base e raised to k is also as it is. Now we differentiate this a raised to lx plus m according to our standard formula, that is a raised to lx plus m into log a, okay, into derivative of lx plus m is L using the composite function rule. Okay, and simplifying this, what we get is yk plus 1 is equal to L raised to k plus 1 multiplying L raised to k and L, and here we get log of a raised to k plus 1 into a raised to lx plus m. Okay, so therefore I can say that pk plus 1 is true, and hence we can say pk implies pk plus 1 is true, and therefore pn is true for every n belongs to n. So thus pk implies pk plus 1 is true. This thing is proved, and therefore pn is true. The given statement p of n is true for every n belongs to n. So what is proved finally is this. Therefore I can say yn is equal to L raised to n into log of a raised to n into a raised to lx plus m, and we have proved that this is true for every n belongs to n. So this way we can prove the formula of any function whose derivative we can find using the principle of mathematical induction for finding the nth derivative. And all other formulas also we are going to prove using PMI in this and the next lecture. Okay, till then, goodbye.